So if you have time response, so let's say consider a transfer function of a first order system, right? So you have C of S divided by R of S is equal to, let's say, A over S plus A. Okay. So here what we have looked at is system response C of S is R of S A over S plus A, right? So try to understand this. Okay, if I say unit step response, this inherently means that the input is what? 1 or 1 over S. Okay, it's a unit step input. You got it?
Are you trying to ask a question?
Yes.
That's what I meant to ask you yesterday. I couldn't think. Is the unit step always going to be 1 over S, or can it vary?
No, it is always going to be. So unit step is essentially step function is this. Okay. So you have this t, right, and this is r of t. All right. You're looking at what is a step function. You have to understand basically unit step function. So what you're looking at is time r of t. Okay. Time goes from 0, 1, 2, 3, 4 to infinity. This is 1, 1, 1, 1, 1. Here this is unit step function. Got it?
Mm-hmm.
So if you plot this, you're going to get this. Right?
Yeah.
Because you see, t equal to 0, it's 1, right? T equal to 1, it is 1, 1, 1. So this is 1. You understand? So this is a unit step function, and if you take the Laplace of this, R of S is 1 over S. Okay, 1 over. It doesn't vary as a function of time because it varies as a function of frequency. Okay, but R of t is written as, think about this, okay? Limit as time tends to infinity or is equal to 0 for t less than 0 is equal to 1 for t greater than or equal to 0. You understand? For anything, for time less than 0, it is 0. You don't see less than 0 here, right? Time is starting at 0. You got it? For anything greater than 1 or positive time, it is 1. You see all 1. You get it? So there are how many points? There are infinite number of points here. 1, 2. You're just joining these points. Okay. You're essentially plotting this 0 and 1. So if you take the Laplace of this, for all practical purposes, what you can say is R of t is equal to 1, right? For unit step function. This is also represented by u of t. Okay, u of t is 1, or R of t unit step function is 1, because we don't deal with negative time. We don't know negative time. Okay, so here, if you take the Laplace of 1, it is simply, if it's a unit step function, it is 1 over s, or R of t is, okay. If it is 5 unit step function, this will be 5, and this will be 5 over s. Alright. So here, this is the unit step response, because this is here. Because the unit step input is a unit step input. All right. If this is a unit ramp, so does this function look like a step? You see that? A ramp. How will a ramp look like?
Ramp will go up and down.
It's like this. This is an upward ramp.
That's a hard. I didn't know what you meant by ramp. But we can talk about that later.
Sure, I'll just mention to you. So here, ramp function is simply tu of t. So you multiply these two.
By time? Yeah. Well, yeah, that. Yeah.
Right?
Yeah.
And if you plot t versus tu of t, you're going to get this.
So
For 0, it is 0, right? For 1, it is 1. 2, it is 2. 3, it is 3. 4, it is 4.
I see what you're saying.
So that's how you get the ramp function.
That is the ramp function. So the Laplace of ramp is, so let's say if you call, if you take the Laplace of tu of t, it will be
So 1 t squared.
no t,
Oh,
s squared.
S squared.
You got it?
Okay.
Similarly, Laplace of t square u of t is, any guesses?
1 over s cubed.
1 over s cubed, yes. This is a parabolic function. You got
So
it?
are you considering the t and the u of t as the same thing?
U of t is the unit function, unit step function, okay?
Yeah, but how are you?
Together they become ramp function. Together this becomes parabolic function.
Yes. Okay.
You got it?
Yeah, I just don't see how you get an s squared because they're two different variables.
Laplace of this is this.
Right.
Laplace of this, or u of t. Laplace of u of t is what?
Just 1 over s.
1 over s. Okay. Right? Laplace of t u of t is 1 over s square. Laplace of t square u of t is 1 over s cube. You just have to solve for that, and this you can get this from table as well. So this function t square will look like this. Okay, so this is u of t. This is t u of t. This is t square u of t. Okay. Right, so let's look at this. Let's continue to look at this. So here, unit step response is this. Now, your unit step time responses will be okay. If you resolve. Now, what you want to really look at is, shall I erase this?
That's our final answer, right?
Hmm?
That's our final answer, right?
Yes. So that is your response. Okay. That is your time response. That is
Yeah, that's the one part.
what you need to look at is, if I plot
You want to plot that function?
t, right,
Okay.
versus c of t. Okay.
First is going positively go down, right?
Your response will look something like this. Okay. And this is essentially 1.
Why is it not going downward?
Hmm?
Why is it not going down? Like, why isn't it like doing it like the other way? Like so, like a.
So if you look at, if you do the plot, you look at t, okay,
It's going to negative infinity.
and c of t,
It is.
it will look like this.
Mhm.
Okay, you substitute values.
Oh, because the CT will come out positive. Okay. I was just focused on that right side of the problem. I didn't consider the whole thing.
In fact, if you solve for this, you're going to get 1 minus e to the power of minus 80. Okay, if you solve for k and k2, or k1 and k2. This is also unit step response. It is just in time domain. This is in frequency domain. Okay. Now, you see why it is, ultimately why it will be 1? Do you see it?
And because eventually E is going to be 0.
Yeah, it is, this thing is going to get 0, right? Because when t goes to infinity, it will be
Negative
1
0.
over, yeah, it will be infinity. This will be 1 over infinity. Okay. 1 over infinity is 0. So it will ultimately be this. When t is 0, this will dominate. Okay. So here we have looked at this. This part is what?
It's like your.
This is the
Sure,
forced
forced.
response. Okay.
Like a force response.
And this is the natural response. So here we define certain performance parameters. Let's say first let me first divide this like this. These are the guidelines, okay? Or you can just say they're simply guides. The actual response or the actual plot is in blue. And it will eventually, it will almost be asymptotic to that one line, okay? So this is 1 over A, 2 over A, 3 over A, and so on. Okay, and this is the time. This is the time axis. This is the response axis. Okay. Now, what you're going to see is we define certain performance parameters. The first thing we define is time constant. Okay, and time constant is simply 1 over A is called the time constant. This is the first one. Second parameter is the rise time. It is the time taken response to final value. Okay. Then you have the last one is the settling time. This is the final response. Okay. And the formula is simple. TR is equal to 4 over A here. Okay. Settling time is, sorry, this is 2.2 over A. And this is 4 over A. Okay. So let's let's look at.
This is that's just for this problem, right? Or is that in general?
It is general.
Okay.
Okay. So this is point 1, and let's say this is point 9. And what you're looking at is
Let's drop in that
I'm gonna reach another number.
Dr. Cindy, I've got a marker if you need one.
sure.
I've got one right here.
No, it's not black. Oh, he's using
Do you care if it's not
No,
blue?
that's fine. That's fine.
No, I thought he was using black. He's using blue. Colorblind, I'm sorry.
Or stupid.
It's okay, I'm black. Wow, Tony. This guy.
Good vibes club.
So try to understand this. The concept itself is actually very interesting and easy to understand. Okay.
Every time he comes off the board, he's standing right where I need.
See, the response itself, you understand the total response, right? You understand what the response is, what your response means. It may seem overwhelming, but it is not. Okay, so just pay attention here. What is happening is you have a system which is defined by this. These are the dynamics of the system. You apply a certain input, and you get the output. All right, and what you're doing in this plot is trying to understand how the system is responding. Any system. Think about an aircraft, right? As soon as an aircraft is at rest here, you understand? When time is 0, you start applying input. Okay, what will the system do?
Slowly increase.
Slowly increase, right? Ultimately, what is its goal to
Reach one.
go? Let's say to reach a particular altitude and stay there. You understand? So what it's going to go through is it's going to go through 2 phases essentially: transient response and steady state response. Okay, so think about what is a transient response?
That would be like
transition.
like a forced response, right?
It's not. All of this is dependent on force response. Otherwise, it's just going to be at rest. Okay.
So I was just gonna say a transient response would be like something's changing. So like your acceleration, your velocity. Things
It's
like that.
transitional in the sense it is ultimately required to do something, right? If you're going to go on the highway, even when you're driving, your ultimate this thing is to go on highway and keep a particular speed, right? And that is the steady. After you start keeping that speed, that is a steady state response. You understand? But your action of starting from 0 to getting there is a transient response. You understand? Okay. So here rise time is what? What do you understand by rise time?
Right. That's your increase in response, right?
Rise time is essentially, and you can correlate this, you have vehicles rated for 0 to 60, right? You understand? How much time this is something like that. The amount of time it takes from 0.1 to 0.9 of the final value.
Why is it 2.2?
Yes, I'll come to that. Okay, that's a very interesting. That's a very apt question. I'll come to that. But you understand the concept of rise time. It's essentially the time taken for a system to go from 0.1 of the final response to 0.9 of the final response. You understand? So why 2.2? So C of t, what is final C of t? Okay, so here TR is what? Final C of t is what? Anybody? Tourist?
So what?
Final C of t?
You said final CUT? It's when T is equal to 1, so it's only 1 over S. That's what you're asking? Okay.
You with me? That's the final, right? That's how much the final value is. You understand?
So that's why rise time can never equal 1, can never go to 1, because the final time has to be 1.
No, this is the time. This is the time, but this is the response. I'm saying what is the final response is 1, right?
Right.
So C 0.1 is 0.1, right? Because C of t is 1. You understand? You with me? This is what? 1 minus e to the power of minus at. To reach this, what is the time it takes?
I forgot. I forgot.
Zero? Or calculate this?
It is from 0 to 1, okay? So it is this, you just solve for this.
Yeah, how do you manipulate that again?
Right, so you 0.1 equal to, what you do is,
I know how to use the ln function.
ln from here. Okay, if you do ln of 0.1 equal to ln of 1 minus e to the power of minus 80. You need to solve for this t. And what is that t? That t is the time taken for the system to go from 0 to 0.1. 0.1 of the final response. You got it? Okay. Similarly, C 0.9 is 0.9, right? And ln of 0.9 is equal to ln of 1 point e to the power of minus 80. So here you have to look at, I'm going to say this as T1, T2. What is T2 minus T1?
TR.
Yes. TR. That is the rise time. Okay. You solve for T2, you solve for T1, and you substitute that here, you're going to get yeah, and this is 2.2 over 8. If you solve for this one.
Can we just solve for 0.1? Just to
Sure. So ln of 0.1 is what?
So negative number.
Yeah, it's a negative number.
Yeah, negative 2.30.
Negative. I'm going to solve here. Okay. Negative
2.30.
2.30. Right. So you're seeing this, right? Equal to. I think how this ln of 1 is 0, right? Isn't it?
Yes.
0, and this is
That would just be AT, right?
right. It will be 80, so it will be plus, right?
Right.
81. Okay, and this might be 2.1. This might be negative. Okay, but you're going to get T1 is equal to 2.31 over 6. Okay. I think that is how I'll solve for you, but this is how you solve for it. Okay.
Could you not have brought that 1 up there before you did the line?
Yeah, that's actually correct. You're right. Yeah, that's a very good one. Okay, I think I agree with you. So if you look at minus 0.9 equal to minus e to the power of minus 80. Good.
Dr. Sunny, you've got written C sub something of T. What is that? C sub T of T?
This one?
Yeah.
Yeah.
This is final.
Oh, it's an F.
F. Okay. Yeah, so you're right. Sorry. So it will be, if I bring this here, it will be minus 0.9, right? Equal to minus e to the power of minus 80 plus plus. Okay. And if you solve for this, I think what you're going to get is, now you take the ln on either side. Okay, this is T1. Tell me ln of 0.9. I think it is 1.1. Sorry, 0.11. I'm guessing.
Yes, 0.11.
Equal to
What was negative 0.11?
Yes, negative 0.11.
negative 0.11, right? It is negative a T1. Okay, and if you solve for this is positive. T1 is 0.11 divided by a. Okay. And similarly, you can solve for this. Here, this will become 1 negative. So T2 will be 0.31. So the difference in those two is the rise time. You got it? So it depends on how you define this rise time as well. If you just define it as 0 to 60 or 0 to 60%, 70%, this will change. The rise time definition will change. Okay. Now similarly, you can do this, right? TS equal to. In chapter 4, we typically deal with this aspect. You got it?
Is it, Dr. Sunny, is that negative natural log of or is natural log of negative 0.1 on the second for time 2?
Right. It is positive. So this is both sides negative, right? So it will become positive.
So they're supposed to be, okay.
It's either both sides negative or both sides positive.
Gotcha.
Okay. The simple application of this is, I'm going to erase this, okay?
No. Actually, here, just let me take a picture.
You're done?
No, I'm just taking a picture. Okay. Okay.
So the example would be the way you utilize it is given G of S is equal to 50 over S plus 50. I'm going to say find time constant TR TS for a unit step response. Okay, so here you're going to do this. You don't have to do anything, but so solution would be, so what is C of S? It is G of S
Over RS.
into R of S, right? And R of S is 1 over S, right? So it is here, it is 1 over S 50 S plus 50. Okay, your C of T is simply 1 minus e to the power of minus 50t. Right. What you're going to realize here is time constant. So what is time constant? It's simply equal to, that is 1 over,
Oh, A.
so compare this to A over S plus A. You should always compare these two, okay? Don't compare these. Don't compare the numerator. Compare the denominator. Alright? So it is 1 over 50. This is 0.02.
You went on a decimal.
Right? What is rise time?
It's 2.2 over A.
2.2 over 50. Okay? Or this is 0.0.
4.
What is the unit?
Wouldn't it be seconds?
Second. That's time. And last is 4 over 50. Settling time.
I think this is a good test question, Dr.
Hmm?
That's what I was thinking.
I think this is a good test question.
0.08. It's a great test question.
But this aspect is not on the test. Okay?
Oh.
The test is next Thursday, right?
Yeah.
Tuesday.
Tuesday. Dang.
You said Thursday, right?
Tuesday. I told Monday or Tuesday. Let's not postpone that because your midterm is immediately. There is.
Tuesday's fine.
I've sent you.
Take home midterm.
Monday or Tuesday. Okay.
Definitely
Tuesday. We could do Monday. Tuesday.
All right. Let's do it Tuesday. Okay. So you got this.
Yeah.
Okay. Now let's quickly look at your homework. What do you want from the homework?
The space.
You understand the concept, right? So this is like figuring out, okay, in 0.044 seconds is going to go from 0.1 to 0.9 of the final response. In 0.08 seconds, it's going to settle. You got it?
Oh no, Dr. Sonny. You put 4 or 5 of these on the test, and
I think you
we
could.
draw the graph.
Yeah, I think you really can incorporate, and then we have to label the graph.
But this is not there on the test. So
we say we use
midterm it
incorporate.
will be there. Yeah.
Oh,
And this should be a build your own test class.
All right. What do you need, Julian and Anthony?
Could you go over the what is it called? The space. Could you go over number 10?
What is it again?
Find the state space representation of a given function if the output is y of t.
What is the given function?
D squared. Well, it's the second.
Number 10, is it?
It's the second derivative dy dt. And there, it's the second derivative.
B squared?
D squared of y over dt squared plus 12 dy dt plus 32y equals 32 u of t. And
Okay,
says-
you want the state space representation of this, right?
Yes.
And the output is y of t,
Yes.
right?
Yes.
So here, what is z1? All these are y of t, okay? Everybody, I hope everybody understands that, right? z2 is y dot of t. Okay, so your second order system, two state variables. z1 dot is what? z2. Okay. z2 dot is y double dot of t, which is equal to what?
Second order.
Minus 12 y dot of t minus 32 y of t plus 32 u of t. Alright, if you do this minus 12, I'm just going to rewrite this. This is simply equal to minus 32 z1 minus 12 z2 plus 32 u of t. Alright, so you can write this as z1 dot z2 dot zero 1 minus 32 minus 12 z1 z2 plus 0 32 u of t. The second part is y, right? Y is what? 0. Is it y of t?
Mm-hmm.
That's it.
Yeah. What else do you?
Very easy. Number 11 is like we just did, but instead they're quadratic formulas. So they have like so examples like s plus 10 times s plus 11. How will we do those? Like what will be our a?
So
in that case?
that one you would just
You need to, if you are given transfer function, convert it to this.
so you'd have to convert it to the differential equation and then find the transfer or the
State space representation.
I think where I got confused personally was like because I did everything else, but because we did in the examples that we did, I don't think we did one where it was like in a differential equation form.
It's all, transfer function, differential equation. For state space, I've been telling you that you have to get it to differential equation. It's directly given in differential equation. It's one step easier. Anything else? That's it? Alright.
So when do you want us to turn this in?
Today?
Like right now or like later today?
Tomorrow, you can turn it in tomorrow.